Hi guys, this is Dr. Bay and here's Bugsy, and today we're going to go over part 1 of pericyclic reactions, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the 7 seas, learning about spectroscopy. Organic chemistry.
A conjugated system is comprised of at least 3 or more adjacent sp2 hybridized atoms that have overlapping p orbitals that pi electrons can flow through. Recall that an sp2 hybridized atom is when it has 3 steric groups around it. The next set of reactions that we're going to learn about consists of conjugated pi systems. Dienes are compounds that contain 2 carbon-carbon double bonds. Depending on how close the pi bonds are, will determine the type of diene it is. A cumulated diene, which is also called an alene, is when the pi bonds are adjacent to one another. The dot in between the 2 pi bonds is denoted as a carbon atom. In a conjugated diene, the pi bonds are separated by only 1 sigma bond. In an isolated diene, the pi bonds are separated by 2 or more sigma bonds. And lastly, in a conjugated enone, which is also called an alpha-beta unsaturated carbonyl, a pi bond is conjugated with the pi bond of a carbonyl group. Conjugated dienes can be formed from allylic halides through an E2 reaction by using a strong, bulky base that follows Hofmann's rule. For example, this allylic alkyl halide can react with KOTBU to form the following diene. And in the next example, a dibromide molecule can react with 2 equivalents of KOTBU to form a diene. Keep in mind that a diene, such as 1,3-butadiene, can have 2 different conformers called either S-cis or S-trans. In this case, the letter S stands for sigma or single bond between the 2 alkene pi bonds. And note that this notation is different from the alkene cis-trans naming, where that indicates the direction of alkene substituents directly connected to the alkene carbon atoms. In an S-trans diene, the 2 pi bonds are pointing in opposite directions. In an S-cis diene, the 2 pi bonds are pointing in the same direction. Now let's learn about a new class of organic reactions that involve conjugated pi systems. Previously, you learned that reactions could proceed through either ionic or radical intermediates. A new category of reactions is called pericyclic reactions that do not involve either ionic or radical intermediates. These pericyclic reactions can be subcategorized into 3 different groups: cycloaddition reactions, electrocyclic reactions, and sigmatropic rearrangements. Each of these reactions has the following features which are characteristic of pericyclic reactions. Each reaction is concerted, which means that there are no intermediates. Second, it involves a ring of electrons moving around in a closed loop. And third, it occurs through a cyclic transition state structure. The 3 types of pericyclic reactions differ in terms of the number and types of bonds that are broken and formed. But for the remainder of this video, we're only going to focus on cycloaddition reactions. The Diels-Alder reaction was discovered by 2 chemists, Otto Diels and Kurt Alder, who won the Nobel Prize in Chemistry in 1950. The Diels-Alder is a type of cycloaddition where a diene and a dienophile react together under a high temperature to form a cyclohexene. It's specifically called a 4+2 cycloaddition, where 4 pi electrons from the diene add to 2 pi electrons from the dienophile to form the 6-membered ring product. Let's number the 4 carbons part of the diene as C1 through C4. And then let's label the dienophile as C5 and C6. The Diels-Alder mechanism is concerted or one step, and all 6 pi electrons move around in a closed loop where single or sigma bonds are formed between C1 and C6, as well as C4 and C5. And note that there is no regio or stereochemistry in the product until you add substituents to either the diene and or the dienophile. Certain substituents can speed up a Diels-Alder reaction. A diene prefers to have an electron donating group or EDG. Some examples of EDGs are alkyl groups, alkoxy groups, and amino groups. Dienophiles, on the other hand, prefer to have an electron withdrawing group or EWG. Some examples of EWGs are CF3, CN, esters, and other carbonyl compounds. Now, if the two groups swapped, where a diene had an EWG substituent or a dienophile had an EDG substituent, then the Diels-Alder reaction would slow down. Now let's take a look at the stereochemistry of a product. If the diene is substituted, the position of the substituents will dictate its stereochemistry. If there are substituents on either C2 or C3 of the diene, they do not affect stereochemistry because they start on an sp2 hybridized carbon and end on an sp2 hybridized carbon. However, if there are substituents on either C1 or C4, then we do have to pay attention to stereochemistry. Substituents on C1 and C4 can either point outside, labeled as out in pink, or the substituents could point inside, shown in green. The two outside groups will end up on the same face as shown as wedged bonds, and the two inside groups will also end up on the same face as shown as dash bonds. In this example, the methyl group on C1, shown in green, is pointing in, so it'll be on a dashed bond in the product. The second methyl group on C4, shown in pink, is pointing out, so it'll be on a wedged bond in the product. Now, if the dienophile is substituted, then there are different rules. The relationship of the substituents bound to a dienophile is preserved in the Diels-Alder product. This means that if the dienophile is cis, where both substituents are pointing in the same direction, then we get a cis product where both substituents are on the same face. If the dienophile is trans, where both substituents are pointing in opposite directions, then we get a trans product where the substituents are anti to one another. Now, in terms of the regioselectivity of a Diels-Alder reaction, there's only one possible regiochemical product if either the diene or the dienophile is symmetrical. In the first example, a symmetrical diene is reacting with a monosubstituted dienophile to get the following product. In this next example, a monosubstituted diene is reacting with a symmetrical dienophile to get the following product. However, if both the diene and the dienophile are unsymmetrical, then there are two possible regiochemical products. In this example, you could get two possible products depending on the orientation of the dienophile, where the aldehyde functional group could either be pointing up to get the first product, or it could flip around to get the second product. But of the two molecules, how do you know which one is the major product? Regiochemical outcomes of a more complicated Diels-Alder reaction can be rationalized if we draw the resonance structures of the diene and dienophile. For the diene, a second resonance contributor could be drawn if one of the lone pairs on oxygen gets pushed to form a double bond and a positive charge on oxygen, and a second arrow from the pi bond forms a new lone pair with a negative charge. Then for the dienophile, the carbonyl pi bond can break to form a new lone pair of electrons on the oxygen atom to form one resonance structure. And then the carbon-carbon pi bond can get pushed to the adjacent bond to form another resonance structure. Now if we label the diene and the dienophile with partial charges found from the resonance structures, the two molecules should orient with one another where the positive and negative charges are aligned. This is because attractive forces are stabilizing and more favorable. Let's keep the diene in the same position. Carbon 1 has a partially negative charge based on the resonance structure, which makes carbon 4 partially positive. Then let's look at the dienophile where the aldehyde group is at the top. The carbon atom closest to the aldehyde is partially negative based on the resonance structures, and the bottom carbon is partially positive. Notice that the partially negatives are lined with one another and the partially positives are lined with one another. Because similar partial charges repel one another, this forms the minor product. Now if we flip the dienophile over, where the aldehyde is now pointing to the bottom, now notice that the positive and negative partial charges are now aligned, and this forms the major product. So in conclusion, there are 4 different types of dienes, but conjugated dienes are the most commonly used in pericyclic reactions. Conjugated dienes can be formed from allylic halides by using an elimination reaction. And lastly, you learned about the Diels-Alder reaction, which is a 4+2 cycloaddition reaction. Its mechanism is concerted, and its rate could increase if there are certain substituents attached to the diene or dienophile. And the product's stereochemistry depends on substituent placement, and its regiochemistry will depend on the alignment of partial charges found through resonance.